Hello, today we shall be deriving the current, voltage, and power divider rules from the above formulas which we derived in part A of this series. If you haven't watched it yet, please click on my channel profile below to watch it under the electricity playlist so that you bring yourself to speed on what we are doing. Starting with this form of the equation for total current, we see that the product is from 1 to n being a positive integer. Let us write the equation in this form because I am trying to convert the series current to a parallel current. Noting that the current through any resistor in the series circuit is equal to the total series current, this equation becomes this. Subbing in this series parallel current relationship produces the following result. Rearranging for IP1 yields this. This is the current divider rule. It may not seem obvious to you at the moment, so let me express it in a familiar form. For two resistors, N is equal to 2. Hence the equation becomes IP1 equal to IP over sigma 2. From our equation for sigma 2 is given as follows. Subbing this in the equation yields this. This is the familiar form of the current divider rule, which states that the current through one resistor in a parallel connection of two resistors is equal to the resistance of the other resistor divided by the sum of their resistances, all multiplied by the total parallel current. It takes a lot of time, energy, and thoughts to produce and edit these videos. Please support this channel by clicking that like and subscribe button. It really counts, so please don't ignore that request, as it will help me to be able to make more videos like this one. The previous equation works only for two resistors, as we saw in part A. To derive a more general form of the current divider rule, we have to use the more general equation for total current, which is this one. Multiplying and dividing the right-hand side of the equation by sigma j yields the following green expression. We have used a different index j just to avoid confusion. Remembering this current relationship, our green equation can be written as follows. This is the more general form of the current divider rule in terms of sigma, but once more, let's express it in a form that you are familiar with. To do that, we need only worry about the term in the bracket. It is given by the following expression, where we have replaced sigma I with the sum of Rj over Ri. Rj is a constant with respect to I, so let's push it out of the summation to have this. For parallel connections, this summation over I is equal to 1 over the equivalent resistance. Also, sigma j can be written as follows. Subbing all this in the purple expression yields the following blue equation. The summations cancel and we have this. This is the familiar and more general form of the current divider rule. Now, let us derive the voltage divider rule. To do that, let's consider the voltage relationship. Note that the voltage through any resistor in a parallel circuit is equal to the supply voltage. So, our voltage relationship can be written as follows. Subbing the expression for sigma I into this equation yields the following equation. This is the voltage divider rule for any number of resistors connected in series. In case you don't recognize it, let's express it in a familiar form. Assuming we have just two resistors, R1 and R2, the voltage drop across R1 is given as R1 over R1 plus R2 times the total voltage. This is the familiar voltage divider rule. Now, let's derive the power divider rule. This rule is not found in any textbook, but my model is able to produce it. It is slightly different for parallel and series type circuits. It provides a shorter and quicker way for circuit analysis. It is a major achievement of this model. Before we continue, please hit that subscribe and like button. Please share this video with friends to support this channel. Getting the power divider rule for series circuits is pretty straightforward. Let's multiply both sides of the voltage equation by the series current Is to have the following expression. On the left, we have the total series current times the total series voltage, which is equal to the total series power. On the right, we have the series voltage drop across one of the resistors times the current through it, which is equal to the power dissipated by that resistor. So this equation becomes PS equal to sigma I times PSI. This is the power divider rule for any number of resistors in series. For two resistors, this rule is given as follows. To get the equation of the power divider rule for parallel circuits, we use the equation for the current divider rule we derived earlier. Multiplying both sides of this equation by V, the supply voltage, we have this. V times IPJ is equal to the power dissipated by resistor J, and IP times V is the total power dissipated. So we can write the equation in the following form. This is the power divider rule in terms of sigma. In terms of resistance, the equation is given as follows by considering just two resistors. Before we dive into examples to validate these formulas, tell me what you think about the model I have presented in the comment section below. Example 1. An electric heater rated 2000 watts is connected in series with a 1000 ohms resistor. If the resistance of the heater is 500 ohms, what is the total power dissipated in the circuit? Let's solve the problem using our traditional method. The circuit diagram is given as follows. Using the expression power equal to current squared times resistance for R1, the expression for the total current is given as follows. Subbing in the values like so yields I equal to 2 amperes. Using the same power equation for I2, P2 is given as follows. So P2 is equal to 4000 watts, and the total power is therefore given by 4 plus 2, which is equal to 6 kilowatts. To solve the problem using the power divider rule, we simply have total power equal to sigma 1 times PS1. Subbing in the values gives the same 6 kilowatts. We have arrived at the same answer in just 2 steps. Tell me what you think about this approach in the comment section below. Let's repeat the same problem, but this time connecting the heater in parallel with the resistor. Let's make a little remark about relative multiples before we move on. It is very easy to calculate the relative multiples of resistors without even writing anything down, because it is simple addition. On the other hand, to calculate the equivalent resistance for parallel connections, especially when there are many resistors, is a very tiring thing. This gives an advantage of using the relative multiple technique over the equivalence resistance technique. Back to our problem. The circuit diagram is given as shown. Like we did before, we use the power equation formula to calculate the current through R1 as follows. This gives us 2 amperes. Power can also be defined as current times voltage. This gives a voltage of 1 kilovolts. To calculate the power dissipated by R2, we can use the formula P equal V squared on R. This gives 1000 squared over 1000, which is equal to 1 kilowatt. Therefore, the total power is given by 1 plus 2, which is equal to 3 kilowatts. Method 2. We simply use the power divider rule P equals sigma 2 times P1, which gives the same 3 kilowatts. I don't know about you, but I think this is a great achievement of this model. Let me know what you think about it in the comment section. Don't forget to subscribe and click the like button if you enjoyed this video. Thank you and hope I see you again.